Okay, the steps of application of dualistic methods. First, change the objective of maximization in the primal into minimization in the dual and vice versa. The first step. The process of application of dualistic method. Change the objective function of maximization in the primal into minimization in the dual and vice versa. Vice versa means to change the objective function of minimization in the primal into maximization in the dual. Step 2. For a maximization primal with less or equal type constraints, there exists a minimization dual problem with all greater or equal type constraints and vice versa. The inequality sign for non-negativity constraint is unreserved. So usually the constraints of maximization are corresponding with the less or equal type. So in case of minimization, these constraints should be converted into type more or equal and vice versa. Okay, the constraints of maximization usually are corresponding by the signs of or the symbol of less or equal. In case of minimization constraints, the symbol or the sign should be more or equal. Step 3. The number of variables, decision variables, in the primal will be the number of constraints in the dual and vice versa. So if the objective function of the primal, for example, has two decision variables, x2, x1 and x2, so the number of these variables are 2, x1 and x2. The number of the constraints of minimization or in the dual version also must equal 2. And the number of constraints of the primal must equal the number of variables in the dual. So the number of variables in the primal equal the number of constraints in the dual, and the number of the constraints in the primal equal the number of variables in the dual. The costs of coefficients C1, C2 up to Cn in the objective function of the primal will be the right hand side constant of the constraint in the dual and vice versa. So usually the objective function states that, for example, max z equals c1 x1 plus c2 x2. These two coefficients c1 and c2 will be the right hand side constant of the constraint in the dual. The constraint of the primal, will be the coefficients of the objective function in the dual. So what that means, we will push the coefficients C1, C2 up to Cn of the primal to the constants of the constraint in the dual, and we will push the constants of the constraint in the primal to the coefficients of variables in the dual. For the constants of the dual, transpose the body matrix of the primal problem. If the ith primal variable is unrestricted in sign, then get dual constant is type is equal type, and vice versa. These are the rules of constructing the dualistic model. Each linear programming has two options: primal and dualistic option. Example: given max z equal 3x1 plus x2 plus x3. So the required is to convert this primal linear programming into the dual linear programming. Now, as you see, the objective function is maximization function. And the coefficient of x1 is 3, coefficient of x2 is 1 and the coefficient of x3 is 1. Subject to this LPP has three constraints: for x1 negative x2 less or equal 8, 8x1 plus x2 plus 3x3 more or equal 12, 5x1 negative 6x3 less or equal 13. So there are three objective or three decision variables: x1, x2 and x3, and there are three constraints respectively. There are three constants as given. Three constants are 8, 12 and 13. We emphasized before that the constraints of maximization must be less or equal. In this case, the constraint number 2 is more or equal. So we need to convert the second constraint into less or equal. How to do that? To do so, we need to multiply each term of the constraint number 2 by negative 1. So, solution. Let y1, y2 and y3 be the dual variables. Then the corresponding dual is mine y equal 8y1 plus 12 8y2 plus 13 8y3. So 8, 12 and 13 are what? 8, 12, 13 are the constant of the constraints of the primal. As we mentioned before, the constant which at the right hand side of the constraints are 8, 12 and 13. So as let's return back. We need to fix if the second constraint is more or equal. We need to fix it as less or equal to be suitable for the maximization problem. But if change this constraint to less or equal, it will be easy to convert the primal table into a dualistic option. Let us assume this. We are going to change technically the second constraint to less or equal. Then we will practice very different cases of the constraints. Now, the objective function now is mine zy or mine y equal 8y1. 8 is the constant of the first constraint plus 12 plus 12 y2. 12 is the constant of the second constraint, and 13 is the constant of the last constraint. It's okay. Now let's move to construct the constraints of the dual. The constraints of the dual are constructed in the following manner. The vertical column, the first vertical column of the primal constraint will be the first row of the constraint in the dual. Let's see. The first column contains of the primal contains 4x1, 8x2 and 5x3 and 5x1. Then the first row of the first constraint of the primal will be 4x1 plus 8x2 plus 5x3 more or equal what? More or equal 3. More or equal 3. 3 is the coefficient of the primal table. And the second constraint will be negative x negative y2 plus negative y2 plus y2 more or equal 1. This constraint, the second constraint, contains two variables because there is no x2 in the third constraint. Okay, and the last constraint will be y1 3y1, check it, 3y1 plus 3y3 plus 3y3 more or equal 1. more or equal 1. So here we need to just check how to use the previous steps in the process of application. Okay, write the dual of the following LPP. Given minimization Zx equal 3x1 negative 2x2 plus 4x3. The constraints are 3x1 plus 5x2 plus 4x3 more or equal 7. So okay. Constraint 2, 6x1 plus x2 plus 3x3 more or equal 4 is okay. 7x1 negative 2x2 negative x3 less or equal 10. This is not okay, because this constraint less or equal, and the constraints of minimization must be more or equal. The first constraint is x1 negative 2x2 plus 5x3 more or equal 3, and the last constraint is 4x1 plus 7x2 negative 2x3 more or equal 2, x1 x2 x3 more or equal 0. Solution. So this primal of minimization has 3 decision variables: x1, x2 and x3. The coefficients of these variables 3, 2 and 4. The constraints are 1, 2, 3, 4, 5. This LPP has 5 constraints, respectively has 5 constants. Now, what is the expectation? Of course, minimization should be converted into maximization, given the coefficient of the dual must contain 7 are 7, 4, negative 10, 3 and 2. Once the primal problem has 5 constraints, respectively has 5 constant, then the number of variables of dual must be 5 variables. And the number of the constraints in the dual must be 3, because the variables in the primal are 3. Let's see. Since the objective function is of minimization type, all inequalities have to be changed to type more or equal. Constraint number 3 will be changed to negative 7x1 plus 2x2 plus x3 more or equal negative 10, and that is now based on the mentioned procedures and steps. The dual LPP should be constructed as follows. Max Z equal 7y1. 7 is the constant, remember, return back. 7 is the constant of the first constraint of the primal. On the right hand side of the first constraint of the primal equal 7. The right hand side of the next constraint in the primal equal 4. So the next variable is the coefficient of the y2 must be 4 plus 4y2. The next coefficient of y3 must be negative 10. So after y negative 10, because the original is less or equal 10. After the transformation we got negative 10. So negative 10y3 plus 3y4. 3 is the constant of the force constraint, plus 2y5. 2 is the last constant of the last constraint. Subject to, let's see, 3y1 plus 6y2 plus negative 2y3 negative 2y4 negative 2y5, and that is let's see, the first constraint is 3y1 plus 6y2 negative 7y3 plus y4 plus 4y5, that is less or equal 3. What is the 3? 3 is the coefficient of x1 in the primal linear programming, and so on. 5y1 plus y2 plus y plus 2y3 negative 2y4 plus 7y5 less or equal negative 2, and 4y1 plus 3y2 plus y3 plus 5y4 negative 2y5 less or equal 4. Check the number of the constraints in the dual R4 R3 equal the number of the decision variables in the dual. Okay, try to obtain the dual of the following LPP. Max Z equal x1 negative 2x2 plus 3x3 subject to negative x1 plus x2 plus 3x3 equal to 2x1 plus 3x2 plus 4x3 equal 1, and xy, x2, x3 more or equal 0. Okay, this is our the dualistic application of the previous primal table. Max z equal 3x1 negative 3x2 plus 6x3 plus 3x4. As we mentioned before, we will get 4 variables because the primal has 4 constraints subject to 3x1 negative 3x2 plus 4x3 negative x4 less or equal 4, x1 negative x2 plus 3x3 negative 2x4 less or equal 1. We got 3 constraints because the primal has 2 variables. The non-objective function contains 3 products: x1, x2, x3, x4. Obviously more or equal 0. Now again let me make stress on the following givens. Recap. Just recap. First, it is not necessary that the primal is to be maximized. Not necessary. It can be minimized too. Did you get it? Yes. That means the dualistic version can take 2 shapes: easier maximization or minimization as a result of the given primal. Now, the maximization problem in the primal، مشكلة التعظيم في الحل في المشكلة الأساسية becomes a minimization problem in the dual. في المقابل تحول مشكلة التعظيم في الأساسية إلى تنمية في المشكلة المقابلة أو الثنائية. And what vice versa. The maximization problem has less than or equal to type of constraints. These constraints of maximization becomes more or equal of minimization state, while the minimization problem are greater than or equal to type of constraints. If primal contains m constraints and n variables, the primal if the primal هو الحل الأساسي، المشكلة الأساسية بتحتوي على m قيود و n متغيرات. If the primal contains m constraints and n variables, then its dual will contain n constraints and m variable. Stress. That is the transpose of the body matrix of primal problem gives the body matrix of the dual and vice versa. Mathematical logic excited. The constants now C1 up to Cn in the objective function of the primal appear تظهر وين whatever in the right hand side of the constraint of the dual. If the constants C1 Cn, by constants we mean easier profit of 1 unit or cost of 1 unit. These constants in the objective function هذه الثوابت في دالة الهدف بتظهر لنا وين؟ بتظهر في الصائد اليمين للقيود as B1 B2 B3 resources of the dual. The constant P1 up to Pm, which on the right side of the constraints are the resources in the constraints of the primal appear in the objective functions in the dual as what? As the coefficients of the decision variable. As the coefficient of decision variable. 6. Both the primal and the dual variables, both the primal and dual variables are non-negative. Are what? Non-negative. Non-negative. Primal are what? Are non-negative. The dual of a linear programming problem find a place in this lecture. The economic interpretation of the dual variables that can be used by management for planning its resources is also explained as from the point of the process of optimization, especially if LPP involving a large number of variables and constraints. That it should be solved using the methods of duality linear programming. But the challenge is how to compare between the findings of the simplex solving of the linear programming of the primal and the dual. How to compare between the finding, between the solution of the primal and the dual, and which give the optimal solution, easier maximization or minimization. Also, we can use the primal methods or using the simplex to solve LPP primal problem to find, for example, the variables x1, x2 up to xn, or s1, s2 up to sn, and to find z. Assume that the problem is maximization of profit, and we found out the values of x1, x2 up to xn, and s1, s2 up to sn, and z. So the combination of x1, x2 should maximize profit. These findings should be compared with the findings of the duality version of minimization. So the comparison between the level of profit maximization and the level of cost minimization. This will be a very advantageous approach and contribution to the problem of duality. Thanks. A summary of the general relationship between primal and dual LPP given in the following table. If primal objective function is to maximize, then dual objective function is to minimize. If primal objective function is to maximize, then dual objective function is to minimize. If primal variables x, j, then dual constraint is j. If primal constraint I, then dual variables y, I. If primal variables x, j unrestricted in sign, then dual constraint j is equal type. If primal constraints I is equal type, then dual variable xi is unrestricted in sign. If primal less or equal type constraints, then dual is more or equal type constraints. If primal xj are restricted in sign, then dual yes constraint is an equation, and that is The dual of the dual LPP is again the primary problem. If easier, if either the problem of the dual has unbounded objective function value, the other problem has no visible solution. If either the problem of dual problem has a finite optimal solution, the other one also possesses the same, and the optimal value of the objective function of the two problems are equal. For example, max zx equal min zy. The analytical result is known as the fundamental primal dual relationship. For complementary slackness property of primal dual relationship states that for a positive basic variable in the primal, the corresponding dual variable will be equal to 0. Alternatively, for non-basic variable in the primal, which is 0, the corresponding dual variable will be basic and positive. The importance of the dual LPP is in terms of the information which provides about the value of the resources. The economic analysis is concerned in deciding whether or not to secure more resources and how much to pay for these additional resources. The significance of the study of dual is as follows. The dual variables provide the decision maker a basis for deciding how much to pay for additional units of resources. And number 2, the maximum amount that should be paid for one additional unit of a resource is shadow price, also called simplex multiplier. Shadow price, also called simplex multiplier. The total marginal value of the resources equals the optimal objective function value. The dual variables equal the marginal value of resources, shadow prices. This is the importance of duality, the importance of dualistic methods or duality. Advantages of duality. It is advantageous to solve the dual of primal having less number of constraints, because the number of constraints usually equals the number of iterations required to solve the problem. To avoid the necessity, it avoids the necessity of adding surplus of artificial variables and solves the problem quickly. The technique is known as the primal dual method. In economics, duality is useful in the formulation of the input and output system. It is also in physics, engineering, mathematics, etc. The dual variables provide an important economic interpretation of the final solution of an LPP. It is quite useful when investigating change in the parameters of an LPP. The technique is known as sensitivity analysis. Duality is used to solve an LPP by the simplex method, in which the initial solution is invisible. The technique is known as dual simplex method. The technique is known as the dual simplex method, as we mentioned before.